66 million years ago, on an ordinary spring morning in what would one day be called the Cretaceous period, a rock the size of a mountain was hurtling toward Earth at 20 kilometers per second. It had traveled for millions of years through the cold silence of space, its trajectory shaped by an almost infinite chain of gravitational interactions, the pull of Jupiter, the nudge of passing comets, the slow wobble of its own spin. None of that history mattered anymore. What mattered was that in approximately 4 hours, this 10-kilometer sphere of carbonite and iron would strike the shallow seas off what we now call the Yucatan Peninsula, and it would change everything. The impact released the energy of 100 million nuclear weapons. It vaporized billions of tons of rock, sulfur, and seawater, launching a cloud of debris into the stratosphere that would circle the globe within hours. Wildfires swept across continents. Tsunamis hundreds of meters high crashed against coastlines thousands of kilometers from the impact site. And then came the darkness, a years-long twilight as the sun vanished behind a shroud of dust and sulfur aerosols, dropping global temperatures by nearly 30 degrees Celsius. The plants died first, unable to photosynthesize, then the herbivores that depended on them, then the predators that depended on the herbivores. Within a geological instant, 3/4 of all species on Earth were gone, including every dinosaur larger than a house cat. That is what happened. That is the history written in stone, in the thin layer of iridium-rich clay that marks the boundary between the Mesozoic and Cenozoic eras, in the 200-kilometer scar buried beneath the sediments of the Yucatan. But tonight, we are going to imagine a different history. We are going to ask what would have happened if that rock, that mountain falling from the sky, had missed. It nearly did, you know, or rather, it nearly could have. The specific trajectory of any asteroid depends on countless variables stretching back billions of years, and a change in any one of them would have produced a different outcome. Some researchers have calculated that if the Chicxulub impactor had arrived just minutes earlier or later, it would have struck deep ocean rather than shallow coastal waters. Less vaporized rock, less sulfur in the stratosphere, a regional catastrophe rather than a global extinction. The dinosaurs would have woken up the next morning to a world shaken but not destroyed, and they would have continued doing what they had been doing for the previous 165 million years, dominating every terrestrial ecosystem on the planet. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and let me know in the comments where you're tuning in from. I'm always curious to see how far these stories travel. Now dim the lights if you haven't already. Take a deep breath and let the modern world fade away. Listen for the sound of wind through Cretaceous ferns, the rustle of a world preparing to continue rather than end. This is the story of 66 million years that never happened, and we're going to walk through every step of it together. The discovery that an asteroid killed the dinosaurs is itself a remarkable story, and it's worth telling briefly because it shows how science works, how a radical idea, dismissed at first as fantasy, can become accepted fact when the evidence accumulates. In 1980, a physicist named Luis Alvarez and his geologist son, Walter, were studying rock formations near Gubbio, Italy, examining the thin layer of clay that marks the Cretaceous-Paleogene boundary. They found something strange, iridium, and lots of it, 30 times the normal concentration. Iridium is rare on Earth's surface because most of it sank into the planet's core billions of years ago when the Earth was still molten, but it's common in asteroids. The Alvarez team proposed that a massive impact had occurred at exactly the moment the dinosaurs disappeared, and they predicted that somewhere on Earth there should be a crater to prove it. The scientific community was skeptical. Many geologists preferred volcanic explanations, The Deccan Traps in India had been erupting for millions of years around the same time, pouring enough lava to cover half of modern India in basalt, kilometers thick. Surely that was enough to explain a mass extinction. But the Alvarezes kept gathering evidence, and other researchers joined the hunt for the crater. In 1978, a geophysicist named Glenn Penfield had noticed something odd while surveying for oil in the Yucatan, a vast circular structure buried beneath the sediments, visible only in gravity and magnetic anomaly maps. He didn't know what it was, but he suspected it might be an impact crater. It took another decade for the connection to be made, for samples from Mexican oil wells to be tested and found to contain shocked quartz and tektites, minerals that form only under the extreme pressures of an asteroid impact. By 1990, the case was closed. The crater was real, it was exactly the right age, and it was exactly the right size to have caused the extinction. But here is the thing about asteroid impacts, the thing that makes our thought experiment possible. They are not inevitable. They are not destiny. They are contingency, pure and simple, the result of orbital mechanics and gravitational perturbations playing out over timescales so vast that the outcome might as well be random. The Chicxulub impactor could have arrived a few minutes earlier and splashed into deep water. It could have arrived a few hours later and struck the middle of the Pacific. It could have missed Earth entirely, sailing past our planet and continuing on into the outer solar system, never to return. In any of those scenarios, the dinosaurs would have survived. Not because they were destined to survive, but because the particular event that killed them simply wouldn't have occurred. Our story begins in that alternative moment. The asteroid screams through Earth's atmosphere, carving a white-hot trail across the sky, visible from 1,000 kilometers away. It strikes the Pacific Ocean 2,000 kilometers from the nearest coastline, generating tsunamis that devastate coastal regions across the Americas and Asia. Millions of creatures die. Ecosystems are disrupted for decades, but the sulfur stays in the ocean. The dust settles within months rather than years. The sun keeps shining. The plants keep growing. And the dinosaurs, the Tyrannosaurs and Triceratops, the Hadrosaurs and Ankylosaurs, the tiny feathered Maniraptorans darting through the underbrush, continue their ancient reign as if nothing had happened. Because for them, nothing significant has happened. They have survived worse. They have survived the volcanic winters of the Deccan eruptions, the gradual cooling of the late Cretaceous, the shifting continents and changing sea levels that have been reshaping their world for millions of years. They are the most successful group of large land animals the planet has ever produced, and they show no signs of decline. Their diversity is at its peak. Their body sizes range from chicken-sized insectivores to 40-ton herbivores. They occupy every ecological niche, from Arctic forests to tropical swamps. They have been doing this for 165 million years, and there is no biological reason why they cannot continue for 165 million more. The world belongs to the dinosaurs. And now, for the first time in Earth's history, we are going to see what they would have done with it. To understand what might have been, we first need to understand what was. We need to step back from the alternative history we're constructing and look clearly at the world the dinosaurs would have continued to inherit, not the simplified version from children's books, not the cinematic monster movie landscape, but the real late Cretaceous Earth in all its complexity and strangeness. Forget the barren volcanic hellscapes that sometimes populate the popular imagination. The world of 66 million years ago was a world of extraordinary abundance, warmer and wetter than anything we know today. There were no ice caps at the poles. Sea levels stood perhaps 170 meters higher than our modern oceans, drowning coastal plains and splitting continents with shallow inland seas. North America wasn't one landmass, but two, divided by a warm waterway called the Western Interior Seaway that stretched from the Gulf of Mexico all the way to the Arctic Ocean. India was an island, drifting northward on its inevitable collision course with Asia. Australia still clung to Antarctica, and both were green with temperate forests. The air itself was different, carbon dioxide levels perhaps 4 times what they are today, oxygen slightly higher, the greenhouse effect keeping the planet warm from pole to pole. Crocodilians lived above the Arctic Circle. Forests grew where Antarctic ice sheets now grind against bedrock. There were no ice caps at the poles. Sea levels stood perhaps 170 meters higher than our modern oceans, drowning coastal plains and splitting continents with shallow inland seas. North America wasn't one landmass, but 2, divided by a warm waterway called the Western Interior Seaway that stretched from the Gulf of Mexico all the way to the Arctic Ocean. India was an island, drifting northward on its inevitable collision course with Asia. Australia still clung to Antarctica, and both were green with temperate forests. The air itself was different. Carbon dioxide levels perhaps 4 times what they are today, oxygen slightly higher, the greenhouse effect keeping the planet warm from pole to pole. Crocodilians lived above the Arctic Circle. Forests grew where Antarctic ice sheets now grind against bedrock. And everywhere, in almost every terrestrial niche you could imagine, there were dinosaurs. The best window we have into this vanished world is a place called the Hell Creek Formation, a layer of rock stretching across Montana, the Dakotas, and Wyoming that preserves the last 3 million years of the Cretaceous in exquisite detail. When paleontologists dig there, they don't just find isolated bones. They find an entire community of life frozen in stone, a complete ecosystem that we can reconstruct with remarkable precision. The ruler of this world was Tyrannosaurus rex, and it's worth spending a moment really seeing this animal as it was, not as the lumbering tail dragger of old reconstructions, but as something far more terrifying and far more beautiful. 12 meters long from snout to tail, 9,000 kilograms of muscle and bone supported on legs built like a sprinter's, designed for explosive acceleration rather than sustained running. A skull large enough to swallow a human being whole, lined with teeth the size of bananas, each one serrated like a steak knife, each one capable of punching through bone as easily as you might bite through an apple. But the most remarkable feature was the eyes. T-Rex had forward-facing eyes set in a skull that was narrow at the front, giving it binocular vision, depth perception, something rare among dinosaurs. A study by vision researcher Kent Stevens calculated that its visual acuity exceeded that of modern hawks, that it could spot prey from 6 kilometers away, that its ability to judge distance was among the best of any animal that has ever lived. This was not a scavenger waiting for something to die. This was an apex predator with the sensory equipment of a precision hunter. But T-Rex was the exception among predators, not the rule. The Hell Creek ecosystem supported a whole range of carnivores filling different niches. Smaller tyrannosaurs that may have hunted in groups, dromaeosaurids with their famous sickle claws, and troodontids, those strange, large-eyed hunters whose brains, relative to their body size, were larger than any other dinosaur group. We'll come back to the troodontids later because they matter enormously to our story. For now, just note that they existed. Small, smart, watching the world with eyes that saw more than most. The herbivores were even more diverse, and among them, one animal dominated so completely that it's hard to overstate its importance: Triceratops. Paleontologist Robert Bakker once estimated that Triceratops bones make up 5/6 of all large dinosaur fossils in late Cretaceous North America, and if that number is even close to accurate, we need to fundamentally reimagine the Cretaceous landscape. Think of the Great Plains before European contact, when bison herds stretched from horizon to horizon, when the ground trembled under millions of hooves, when you could travel for days without seeing anything but grass and grazing animals. Now replace every one of those bison with a 3-horned, 9-meter-long tank weighing up to 9,000 kilograms, with a skull that made up 1/3 of its entire body length, with horns that could gore a tyrannosaur and a frill of solid bone protecting its neck. That was Triceratops, the Cretaceous equivalent of the American bison, except armored like a medieval knight. Alongside Triceratops lived the Hadrosaurids, the duck-billed dinosaurs, with their remarkable dental batteries, hundreds of interlocking teeth stacked in columns, constantly being replaced, capable of grinding tough vegetation in a way that no other dinosaur group had achieved. There was Ankylosaurus, the armored fortress, its body covered in bony plates called osteoderms, its tail ending in a club of fused bone that could shatter a predator's leg with a single swing. There was Pachycephalosaurus, with its dome of solid bone atop its skull, possibly used for head-butting contests like modern bighorn sheep, though paleontologists still argue about this. And there were dozens of smaller species, each filling its own niche in the ecosystem. Small ornithopods browsing in the undergrowth, oviraptorosaurs tending their nests, tiny mammals scurrying through the leaf litter at night. Above this world flew the pterosaurs, and we need to pause here because the pterosaurs are not dinosaurs. They're a separate lineage entirely, related but distinct, like cousins rather than siblings. The largest of them was Quetzalcoatlus, named after the Aztec feathered serpent god. And when I tell you that its wingspan reached 11 meters, I need you to actually picture that. Wider than a small airplane, larger than any flying animal that has ever existed before or since. Standing on all fours, it would have looked a giraffe in the eye. Yet its bones were hollow, honeycombed with air pockets, so lightweight that this creature the size of a small aircraft probably weighed only about 250 kilograms. Less than many adult humans. It probably hunted like a giant stork, stalking across floodplains on folded wings, snatching up small dinosaurs and mammals and fish with a beak the length of a human arm. And what about the mammals? They were there. They had been there all along, evolving alongside the dinosaurs from the very beginning, sharing the planet for over 150 million years. But they were small. The largest known Cretaceous mammal was perhaps the size of a badger. Most were the size of mice or rats, creeping through the underbrush, climbing trees at night, hunting insects and seeds in the ecological shadows cast by the giants. They were not failures, they were highly successful at what they did. But what they did was stay out of the way. The niches they occupied were the niches the dinosaurs didn't want. The nocturnal niche, the burrowing niche, the tiny insectivore niche. Everything else belonged to the ruling reptiles. This was the world on the morning the asteroid missed, a world of warmth and abundance, of continental drift and shallow seas, of theropod hunters and ceratopsian herds and pterosaurs soaring on thermals above it all. A world that had been refining itself for over 165 million years, that showed no signs of decline, that was, if anything, at the peak of its diversity and success. The dinosaurs weren't waiting to be replaced. They weren't evolutionary dead ends, stumbling toward inevitable extinction. They were the most successful group of large land animals the planet had ever produced, and they had every reason to expect that their reign would continue indefinitely. It almost didn't, of course. In our timeline, the rock from space ended everything. But in the timeline we're exploring tonight, the rock splashed harmlessly into the Pacific, and the dinosaurs woke up the next morning to continue what they had been doing for 165 million years. The question now is, what would they have done with another 66 million years of evolution? What would they have become? To answer that, we need to understand something that the dinosaurs themselves couldn't have known. The world was about to change. Not suddenly, not catastrophically, but slowly and inexorably over tens of millions of years. The warm, stable climate of the Mesozoic was ending. A long cooling was coming, driven by the slow drift of continents, by the rise of mountains, by the circulation of ocean currents that would eventually lock Antarctica in ice. New plants were evolving, grasses, which would spread across the world and transform every ecosystem they touched. The dinosaurs were about to face challenges they had never encountered in 165 million years of evolution. Challenges that would test their adaptability in ways the asteroid never could. But first, let's look at why the dinosaurs were so dominant in the first place, and why the mammals couldn't seem to break out of their ecological shadows. The answer isn't what you might think. There's a story that gets told in countless documentaries and textbooks, a comfortable narrative that explains why the world looks the way it does today. It goes something like this: the dinosaurs were lumbering, cold-blooded failures, evolutionary dead ends that dominated only because nothing better had come along yet. They were big and dumb, slaves to their instincts, unable to adapt to changing conditions. When the asteroid struck, it simply cleared the stage for the true inheritors of the Earth, the mammals, warm-blooded and intelligent, who had been waiting patiently in the wings for their moment to shine. The extinction was almost a mercy, a necessary reset that allowed evolution to finally get things right. This story is almost entirely wrong, and understanding why it's wrong is essential to understanding what would have happened if the dinosaurs had survived. The dinosaurs were not failures waiting to be replaced. They were an evolutionary triumph of staggering proportions, arguably the most successful group of large land animals the planet has ever produced. They dominated terrestrial ecosystems for over 165 million years. Try to wrap your mind around that number for a moment. Anatomically, modern humans have existed for perhaps 300,000 years. The entire genus Homo, including all our extinct relatives, goes back maybe 2.5 million years. The dinosaurs reigned for 66 times longer than that. They evolved into thousands of species, filled every conceivable ecological niche from tiny insectivores to 40-ton browsers, spread across every continent, adapted to every climate from tropical rainforests to polar winters. And they showed absolutely no signs of decline in the millions of years before the asteroid struck. If anything, their diversity was increasing. The late Cretaceous was not a period of dinosaurian senescence, it was a golden age. So why did mammals stay small? Why, after 150 million years of coexistence with dinosaurs, hadn't they produced anything larger than a badger? The traditional answer is simple. The dinosaurs were suppressing them. The big niches were occupied by big dinosaurs, and the mammals simply couldn't compete. They were forced into the margins, into the night, into burrows and treetops where the giants couldn't follow. Remove the dinosaurs, and the mammals would explode into all that newly vacant ecological space. This explanation has a certain intuitive appeal, but recent research suggests it's incomplete at best and possibly backward. A 2021 study from Oxford and Birmingham universities analysed the evolutionary constraints on different mammal groups before and after the KPG extinction, using sophisticated statistical methods to identify where each lineage was hitting ecological limits. What they found was surprising. The ancestors of modern placentals and marsupials, the groups that would eventually produce everything from whales to elephants to humans, weren't primarily competing with dinosaurs. They were being outcompeted by other mammals. The Mesozoic wasn't just home to the tiny shrew-like creatures we usually imagine when we think of early mammals. It hosted a remarkable diversity of mammalian lineages, most of which are now completely extinct. Multituberculates, Gondwanatheres, Eutriconodonts, Dryolstoids. These animals had already claimed many of the small to medium body size niches. Some were gliders, some were swimmers, some were burrowers. Some had teeth specialized for cracking hard foods, others for slicing meat, others for grinding plants. The ancestors of modern mammals weren't being held back by distant dinosaurian giants. They were being outcompeted by their own closer relatives, by other mammals that were simply better adapted to Mesozoic conditions. Think about what this means for our alternative timeline. When the asteroid didn't strike, the dinosaurs continued, yes, but so did these other mammal groups. The multituberculates, which in our timeline survived the extinction and persisted for another 30 million years before finally dying out, would have kept competing with the ancestors of rodents. The Gondwanatheres would have kept occupying the niches that marsupials might otherwise have filled in the southern hemisphere. The playing field wouldn't have been cleared. The mammals that eventually gave rise to elephants and primates and humans would have remained trapped in the same competitive squeeze they had experienced for 150 million years, pressed from above by dinosaurs and from the sides by their own kind. But let's go deeper. Let's ask why the dinosaurs were so good at being large in the first place, because the answer reveals something fundamental about the constraints our alternative history would have operated under. Dinosaurs had a respiratory system that mammals simply cannot match. Like modern birds, which are, after all, living dinosaurs, they breathed using a system of unidirectional airflow through rigid lungs supplemented by air sacs that extended throughout their bodies, even into their bones. When a mammal breathes, air flows into the lungs and then back out the same way, mixing fresh oxygen-rich air with stale carbon dioxide-rich air. It's inefficient. When a dinosaur breathed, air flowed in one direction only, passing over the gas exchange surfaces continuously, extracting far more oxygen per breath. This is why birds can fly over Mount Everest while mammals gasp for air at base camp. This is why sauropods could grow to 50 tons, while the largest land mammals have never exceeded 20. The dinosaurs weren't just occupying the large body niches. They were physiologically superior at being large. They also had hollow bones, pneumatized with air pockets connected to their respiratory system, making their skeletons lighter relative to their strength than any mammal could achieve. They had faster growth rates, reaching adult size in years rather than the decades required by similarly sized mammals. They laid eggs, which meant they didn't have to carry their developing young inside their bodies. A pregnant sauropod would have been a biomechanical impossibility, but an egg-laying one could produce dozens of offspring per year. Every aspect of their biology was optimized for the ecological roles they had been filling for 165 million years. A mammal trying to evolve into a large herbivore in this world would have faced competitors who could breathe more efficiently, grow faster, reproduce more quickly, and carry less weight per unit of structural strength. It's not that mammals were inferior as a group, they were simply trying to compete in a game where the rules favored a different body plan. Put mammals in the ecological vacuum left by the KPG extinction, give them 66 million years without competition, and they'll produce elephants and whales and giant ground sloths. Keep the dinosaurs around and the mammals will remain what they had always been: small, nocturnal, ecologically marginal. This is the world our alternative timeline inherits. Not a world where dinosaurs are fragile relics clinging to existence, but a world where they are the undisputed masters of every terrestrial ecosystem, where their biological advantages make them essentially unassailable in the niches they occupy, where mammals are locked into their traditional roles by competitive pressure from multiple directions. The dinosaurs didn't win their throne by accident or by default. They won it by being extraordinarily good at what they did, and nothing about the asteroid's near miss would have changed that. But here's where the story gets interesting. The dinosaurs' dominance was built on a foundation of stable, warm climate that had persisted throughout the Mesozoic era. For 165 million years, the Earth had been a greenhouse world, warm from pole to pole, humid, forested, with relatively little seasonal variation. The dinosaurs had evolved in this world and were exquisitely adapted to it. They had never faced an ice age. They had never seen a grassland. They had never experienced the kind of dramatic climate swings that would characterize the coming Cenozoic. The world was about to change in ways the dinosaurs had never encountered. The continents were drifting into new configurations, opening ocean gateways that would alter circulation patterns around the globe. Antarctica was separating from South America, and within a few million years, a cold current would begin circling the southern pole, isolating an entire continent and seeding it with ice. The Himalayas were about to rise as India crashed into Asia, their weathering rocks drawing carbon dioxide from the atmosphere and cooling the planet. Grasslands were about to spread across continents, creating entirely new ecosystems with entirely new selective pressures. The dinosaurs had proven themselves masters of the Mesozoic world. The question that our alternative history must answer is whether they could have mastered the Cenozoic world too, a world colder, drier, more seasonal, more variable than anything they had experienced in their long evolutionary history. A world that would have tested their adaptability in ways the asteroid never did, that would have demanded innovations their lineage had never before been required to produce. They had 66 million years to find out. Let's see what they might have done with them. 10 million years have passed since the asteroid missed, and if you could somehow travel back to this world, you might not notice anything different at first. The continents haven't moved much. Continental drift operates on timescales of centimeters per year, and 10 million years isn't enough to rearrange geography in any dramatic way. The climate is still warm, still humid, still tropical even at high latitudes. The forests still stretch from pole to pole, dense and green and dripping with moisture. It looks at first glance like the Cretaceous world we left behind. But evolution doesn't stand still, even when the world seems unchanged. 10 million years is an enormous span of time, longer than the entire existence of the genus Homo, longer than the time separating the first stone tools from the smartphone in your pocket. Species don't remain static over such periods. They drift, they adapt, they specialize, they diverge. The dinosaurs of 10 million years post-asteroid would not be identical to the dinosaurs of the Cretaceous, even if their world remained superficially the same. The most significant change in this period wouldn't have been the dinosaurs themselves, but the plants they depended on. The flowering plants, angiosperms, had been spreading throughout the Cretaceous, diversifying and competing with the older conifers and ferns that had dominated Mesozoic forests. Without the catastrophic disruption of the extinction event, this process would have continued unabated. The angiosperms had advantages that made their eventual dominance almost inevitable. They could reproduce faster, evolve more quickly, form more intimate relationships with pollinators and seed dispersers. By 10 million years after our divergence point, they would have conquered most of the world's forests, and many of them would have been bearing fruit. Fruit is one of evolution's great innovations, a bribe offered by plants to animals. Eat this sweet, nutritious flesh, and carry my seeds somewhere else in your gut. Deposit them with a pile of fertilizer. Give them a head start in life. It's a strategy that works spectacularly well, which is why it evolved independently in so many plant lineages. In our timeline, the explosion of fruit-bearing plants in the early Cenozoic helped drive the evolution of fruit-eating mammals, the primates who would eventually give rise to us. In our alternative timeline, the same opportunity would have been available, but the animals best positioned to exploit it wouldn't have been mammals. They would have been dinosaurs. The Maniraptoran theropods, the lineage that includes dromaeosaurids, troodontids, oviraptorosaurs, and the ancestors of modern birds, were already showing adaptations that would have served them well in fruit-rich forests. They had grasping hands, capable of manipulating objects and gripping branches. Many of them had forward-facing eyes that provided binocular vision, useful for judging distances when reaching for food or leaping between trees. They were small enough to climb, light enough to venture onto branches that would have snapped under the weight of a larger dinosaur. And some of them, the Oviraptorosaurs in particular, had already evolved toothless beaks that might have been well suited for processing fruit and seeds. Picture a descendant of this lineage, 10 million years into our alternative timeline. It's small, perhaps the size of a modern howler monkey, covered in a coat of colourful feathers that serve both for insulation and display. Its hands retain the 3 clawed fingers of its theropod ancestors, but they've become more dexterous, more capable of fine manipulation. Its beak has evolved a slight hook at the tip, useful for tearing open tough-skinned fruits. It lives in the canopy of the flowering forests, leaping from branch to branch, feeding on the bounty that the angiosperms provide. This creature is speculation, of course. We cannot know exactly what forms evolution would have produced in an alternative timeline. But it's speculation grounded in real evolutionary trends, in adaptations that were already present in Cretaceous maniraptorans, in ecological opportunities that would genuinely have existed. The flowering forests would have rewarded any lineage capable of exploiting them, and the small maniraptoran theropods were better positioned to do so than any mammal of the period. But not all the changes would have been in the canopy. Down on the forest floor, the great herbivorous dynasties of the Cretaceous would have been continuing their own evolution, responding to the changing composition of the plant communities they depended on. The Hadrosaurids, the duck-billed dinosaurs, had evolved the most sophisticated plant processing equipment of any dinosaur lineage. Dental batteries containing hundreds of interlocking teeth, constantly being replaced, capable of grinding tough vegetation with an efficiency that no other dinosaur could match. As the flowering plants spread, with their different textures and nutritional profiles, the Hadrosaurids would have adapted right alongside them. Some lineages might have become more specialized, focusing on particular types of plants in particular habitats. Others might have become more generalized, capable of thriving on whatever vegetation was available. The key point is that they wouldn't have stood still. Evolution never does. The ceratopsians too would have continued their radiation. In the late Cretaceous, they had already diversified into dozens of species across North America and Asia, varying in size from dog-sized to elephant-sized, sporting an astonishing variety of horn and frill configurations. Without the extinction, this diversity would have continued to expand. Perhaps some lineages would have become larger, filling niches that in our timeline would eventually be occupied by elephants and rhinoceroses. Perhaps others would have become smaller, more nimble, adapted to different habitats or different food sources. And the sauropods, those long-necked giants that had defined the Jurassic but seemed to be declining in diversity by the late Cretaceous, would have persisted as well. They were specialists, reaching food sources that no other herbivore could access, and as long as tall forests existed, they would have had a role to play. In our timeline, the extinction removed them before we could see how they might have adapted to a changing world. In our alternative timeline, they would have had the chance to prove their staying power. The world of 10 million years post-asteroid would have been recognizable to a visitor from the Cretaceous, but it would have been subtly different in 1,000 small ways. New species where old ones had been. New behaviors, new ecological relationships, new forms filling new niches. The dinosaurs weren't changing because the world forced them to change. The world was still warm, still forested, still fundamentally Mesozoic in character. They were changing because that's what life does. It explores possibilities, it fills available space, it diversifies. But the real changes were coming. Around 55 million years ago, the planet was about to experience something unprecedented, a sudden, dramatic warming that would push global temperatures to levels not seen in tens of millions of years. The Paleocene-Eocene thermal maximum was approaching, and it would test the dinosaurs in ways they had never been tested before. The question was whether they were ready. Around 55 million years ago, something extraordinary happened to the Earth's climate. Within perhaps 20,000 years, a blink of an eye in geological time, global temperatures spiked by 5 to 8 degrees Celsius. The polar regions, already warm by modern standards, became positively tropical. Palm trees grew in Alaska. Crocodilians basked on the shores of the Arctic Ocean. The deep oceans warmed by several degrees, fundamentally altering circulation patterns and marine ecosystems around the world. Scientists call this event the Paleocene-Eocene thermal maximum, or PETM, and it was one of the most dramatic climate shifts in the last 100 million years of Earth history. The cause was almost certainly a massive release of carbon into the atmosphere, perhaps from volcanic activity associated with the opening of the North Atlantic, perhaps from the destabilization of methane hydrates on the ocean floor, perhaps from some combination of both. The result was a greenhouse effect more intense than anything the dinosaurs had experienced since the Triassic. It was a test, and in our timeline, it reshaped mammalian evolution dramatically. Many species went extinct, others shrank in size because smaller bodies are easier to cool. New lineages appeared, adapted to the hothouse conditions. The primates that would eventually give rise to monkeys and apes first appear in the fossil record right around this time, as if the thermal crisis had opened new ecological doors even as it closed others. In our alternative timeline, the same crisis would have occurred. The PTM was driven by geological processes that had nothing to do with the asteroid impact, but it would have been dinosaurs, not mammals, facing the challenge. And here's the interesting thing: dinosaurs might have been better equipped to handle extreme heat than mammals were. Think about the problem from a physiological perspective. Mammals are endotherms. They generate their own body heat internally and work hard to maintain a constant internal temperature, usually around 37 degrees Celsius. This is metabolically expensive and requires sophisticated cooling mechanisms. Sweating, panting, seeking shade, restricting activity to cooler parts of the day. When ambient temperatures approach or exceed body temperature, these mechanisms become less effective. A mammal in extreme heat is working against thermodynamics, trying to dump heat into an environment that doesn't want to accept it. Large dinosaurs operated differently. They were probably gigantotherms. Their sheer mass meant that their body temperature remained relatively stable regardless of external conditions, like a massive water tank that takes hours to warm up or cool down. They didn't need to generate as much metabolic heat as mammals because they could absorb heat from their environment during the day and retain it through the night. And because they didn't maintain the high constant temperatures that mammals require, they weren't as vulnerable to overheating when the world got hot. The smaller dinosaurs had their own advantages. Many of them were feathered, and feathers are remarkably versatile insulators. They can be fluffed up to trap warm air in cold conditions, or sleeked down and spread to allow heat dissipation in hot conditions. The same structure that would later help dinosaurs survive polar winters might have helped them survive equatorial summers during the PETM. The tropical regions during the Eocene hothouse might have become challenging even for dinosaurs, perhaps forcing migrations toward the poles, perhaps creating equatorial dead zones where temperatures simply exceeded what any large land animal could tolerate. But the poles themselves would have become paradise. Warm, wet, covered in lush forests, extending nearly to the Arctic and Antarctic circles. Perfect habitat for dinosaurs of all sizes, expanding into regions that had previously been marginal. But the land wasn't the only arena where evolution was playing out. In the oceans, our alternative timeline would have featured something that our actual history lacks entirely: the continued evolution of the great Mesozoic marine reptiles. In our timeline, the mosasaurs and plesiosaurs went extinct at the KPG boundary, victims of the same catastrophe that killed the land dinosaurs. The niches they left empty would eventually be filled by whales, which evolved from land-dwelling mammals over the course of the Eocene, one of evolution's great transformations. But in our alternative timeline, the marine reptiles never went extinct. They would have been there, already occupying those niches when the PTM reshaped the oceans. The mosasaurs of the late Cretaceous were at their peak, massive sea lizards, some reaching 15 meters in length, with powerful jaws and paddle-like limbs. They were the apex predators of the shallow seas, filling roles similar to modern great white sharks and orcas. Without the extinction, they would have continued to evolve. Some lineages might have become more streamlined, faster, better adapted to hunting fish and squid in the open ocean. Others might have grown larger still, exploiting the abundant marine life of the Eocene hothouse. And the plesiosaurs, those strange, long-necked marine reptiles that had persisted for over 135 million years before the asteroid ended them, would have continued their own strange evolutionary journey. Their body plan, with 4 large flippers and a neck that could be longer than the entire body of many other animals, seems almost absurdly impractical to modern eyes. Yet it worked well enough to sustain them through the Jurassic and Cretaceous. Perhaps in the warming oceans of the Eocene, some plesiosaur lineages would have become more efficient hunters, their long necks evolving as ambush weapons, striking at schools of fish from unexpected angles. Perhaps others would have become filter feeders, straining plankton from the warming waters the way baleen whales do today. The point is that the oceans of our alternative timeline would have looked fundamentally different from the oceans of our actual history. Instead of whales and dolphins and seals, all descended from land mammals that returned to the sea, we would have seen the continued diversification of lineages that had been marine for hundreds of millions of years. The ecological niches would have been similar, but the animals filling them would have been unrecognizably different. On the coastlines, where land met sea, another group would have been thriving, the pterosaurs. In our timeline, they went extinct alongside the dinosaurs, leaving the skies to the birds. But in our alternative history, they would have persisted, and the warm, productive seas of the Eocene would have been ideal habitat for them. Picture a pterosaur the size of a small airplane, soaring over tropical waters, plucking fish from the surface with a beak the length of a human arm. Picture colonies of smaller pterosaurs nesting on sea cliffs, filling the ecological roles that seabirds occupy in our world. Picture the skies of the Eocene shared between the pterosaurs and the birds, both dinosaur lineages, technically, but so different in form and history that they would have competed for some niches while dividing others. The Eocene hothouse lasted for millions of years, long enough for evolution to produce countless adaptations to its conditions. Somewhere around 50 million years ago in our alternative timeline, the dinosaurs would have reached a kind of equilibrium with this warm world, diversified across every continent, dominant in nearly every terrestrial and aerial niche, sharing the oceans with their marine reptile cousins. It might have seemed to an observer at that moment that this was simply how the world worked, that dinosaurs were as permanent a feature of the Earth as the mountains and seas. But the climate doesn't stay constant forever. Even as the dinosaurs were flourishing in their hothouse Eden, the processes that would end it were already underway. India was crashing into Asia, raising the Himalayas, and the weathering of those new mountains would begin drawing carbon dioxide from the atmosphere. Antarctica was drifting toward the South Pole, and soon a new ocean current would isolate it from the warmth of the tropics. The long cooling was about to begin, and it would transform the Earth more profoundly than any asteroid ever could. The warmth couldn't last forever. Around 34 million years ago, the Earth began a long, slow slide toward colder conditions that would eventually culminate in the ice ages of the Pleistocene. The immediate trigger was Antarctica. For millions of years, the southern continent had been connected to South America by a narrow land bridge, and warm ocean currents from the tropics had been able to reach its shores, keeping it relatively mild despite its polar position. But as the continents drifted apart, a new ocean current formed, the Antarctic Circumpolar Current, that isolated Antarctica from the warmth of the rest of the world. Ice sheets began to form on the continent for the first time in hundreds of millions of years. The planetary thermostat had been turned down, and it would never fully recover. The effects rippled outward from the poles. Global temperatures dropped by several degrees. Sea levels fell as water became locked up in Antarctic ice. Rainfall patterns shifted as the temperature gradients between equator and poles steepened. And the forests, those endless pole-to-pole forests that had characterized the age of dinosaurs, began to retreat. This was something new. For 150 million years since before the first dinosaur walked the Earth, the planet had been a greenhouse world, warm and wet, covered in vegetation from the Arctic to the Antarctic. Dinosaurs had evolved in this world, diversified in this world, conquered every continent in this world. They had never faced a planet where ice sheets covered significant portions of the land, where winters could be genuinely harsh, where forests gave way to something else entirely. The Oligocene cooling was a test unlike any they had experienced before. But here's where we need to challenge a common assumption. We tend to think of dinosaurs as tropical animals, creatures of warm climates that couldn't possibly survive in cold conditions. After all, they're often depicted in steaming jungles, their massive bodies soaking up the warmth of a prehistoric sun. And the comparison to modern reptiles seems to reinforce this impression. Snakes and lizards don't do well in cold climates, which is why you don't find them in Antarctica. The problem with this assumption is that it's almost certainly wrong. We now know that dinosaurs lived in polar regions during the Mesozoic. Fossil sites in Alaska and Antarctica have yielded dinosaur bones from latitudes that would have experienced months of winter darkness, temperatures that regularly dropped below freezing. These weren't occasional visitors or lost wanderers. They were established populations, breeding and raising their young in conditions that we would consider harsh by any standard. The famous Prince Creek Formation in northern Alaska preserves a diverse dinosaur ecosystem from about 70 million years ago, including hadrosaurs, ceratopsians, and tyrannosaurs, all living year-round above the Arctic Circle. How did they do it? The answer was literally covering their bodies. Feathers. We've known for decades now that many dinosaurs were feathered, not just the small, bird-like theropods, but a surprisingly diverse range of species. Feathers have been found on tyrannosaurs, on ornithischians, on dinosaurs large and small from lineages across the family tree. The original function of feathers wasn't flight, it was insulation. They evolved to keep dinosaurs warm, to trap body heat against the skin, to allow these animals to remain active in conditions that would have sent a naked reptile into torpor. In our alternative timeline, this adaptation would have proved crucial as the world cooled. The feathered theropods, already equipped with nature's most versatile insulation, would have been able to expand into colder habitats as the ice advanced. Picture a pack of medium-sized theropods, their bodies covered in thick plumage that ruffles in the frigid wind, hunting across a snowy landscape that would have been unthinkable in the Mesozoic. These creatures would have looked remarkably bird-like because they were essentially birds that had never given up hunting on the ground. The larger dinosaurs faced a different challenge. A 15-meter sauropod couldn't rely on feathers for insulation the way a 2-meter theropod could. The The surface area to volume ratio doesn't work in their favor. But gigantothermy cuts both ways. The same thermal inertia that helped large dinosaurs survive the Eocene heat would have helped them survive moderate cold. Their massive bodies would have changed temperature so slowly that short cold snaps wouldn't affect them much. They might have migrated seasonally, following the warmth and the food, the way many large mammals do today. Or they might have simply become restricted to equatorial regions, ceding the higher latitudes to their smaller, more adaptable relatives. The Ornithischians, the Ceratopsians, Hadrosaurs, and Ankylosaurs present an interesting question. We don't have direct evidence that they were feathered, though some specimens suggest they had filamentous integuments that might have served a similar purpose. In our alternative timeline, the selective pressure of cooling climates might have driven the evolution of thicker, more insulating body coverings in these lineages. Picture a ceratopsian of the Oligocene, its body covered in a dense coat of proto-feathers. Its massive frill perhaps reduced from the elaborate displays of its Cretaceous ancestors to something more practical, more streamlined against the cold. It would have looked something like a woolly rhinoceros, but with the unmistakable silhouette of a horned dinosaur. But the most profound change wasn't in the dinosaurs themselves, it was in the world they inhabited. As the climate cooled and dried, the endless forests began to break up. Trees require certain minimum temperatures and rainfall amounts to thrive, and as these conditions retreated toward the equator, the forests retreated with them. In their place, something new was appearing. Open landscapes, woodlands with gaps between the trees, meadows and clearings where sunlight reached the ground. These weren't yet the great grasslands that would later transform the planet, but they were the beginning of something. The age of forests was drawing to a close, and the age of open spaces was beginning to dawn. For dinosaurs that had spent 150 million years in forests, this was a profound environmental shift. The rules of survival were changing. In a forest, you can hide, you can ambush prey or avoid predators by staying out of sight. Size matters less than stealth, and speed matters less than maneuverability. But in an open landscape, there's nowhere to hide. You survive by being fast enough to escape, or big enough to fight, or vigilant enough to spot danger before it's too late. Herding becomes an advantage, because many eyes are better than two. Long-distance running becomes more valuable than short sprints. These are exactly the pressures that would reshape mammal evolution in our timeline, producing the horses and antelope, the wolves and big cats that came to dominate open ecosystems. In our alternative timeline, the same pressures would have acted on dinosaurs. The results might have been startlingly similar, not because dinosaurs would have evolved into mammals, but because the same ecological problems tend to produce similar solutions. A fast-running herbivore is a fast-running herbivore, whether it's a horse or an ornithomimid. A pack-hunting predator is a pack-hunting predator, whether it's a wolf or a derived theropod. The Oligocene was a transition, a bridge between the warm forests of the Eocene and the grasslands that were coming. The dinosaurs that emerged from it would have been different from their Cretaceous ancestors, better adapted to cold, better adapted to open spaces, beginning to develop the specializations that the new world would demand. They had survived their first major test, but the real transformation was still to come. Around 23 million years ago, a humble family of plants would begin a conquest that would reshape every continent except Antarctica. Grass was about to change everything. Grass doesn't seem like a revolutionary organism. It's humble, low to the ground, easily overlooked. You walk on it, mow it, forget it exists. But starting around 23 million years ago, in the early Miocene, grass began a conquest that would transform the face of the Earth more thoroughly than any asteroid impact. By the time it was done, grass would cover roughly 40% of the planet's land surface, and create entirely new ecosystems that had never existed in the first 400 million years of life on land. To understand why grass was so revolutionary, you need to understand what makes it different from other plants. Most plants grow from their tips, damage the top of a tree, and you've removed its growing point, stunted its development, perhaps killed it entirely. But grass grows from its base. You can cut it, burn it, graze it down to stubble, and it simply regrows from below. This makes grass almost impossible to kill through browsing or fire. It's the plant equivalent of a hydra. Remove its head and it grows right back. Grass also produces silica phytoliths, microscopic particles of glass embedded in its tissues. These make grass tough, abrasive, difficult to digest. Any animal that tries to eat grass is essentially chewing on sandpaper, wearing down its teeth with every bite. In our timeline, this drove the evolution of hypsodont teeth, the high-crowned, continuously growing teeth that characterize horses, cattle, and other grazing mammals. Animals that couldn't evolve solutions to the grass problem simply couldn't exploit the new grassland ecosystems. They were locked out of one of the planet's great ecological opportunities. The spread of grasslands was driven by the same cooling and drying that had begun in the Oligocene. As rainfall decreased across the continental interiors, forests retreated to wetter areas near coasts and rivers. The open spaces between them filled with grass, not because grass preferred those conditions, but because grass could tolerate them when trees couldn't. Grasslands are, in a sense, the vegetative equivalent of tough survivors, colonizing the marginal lands that nothing else can hold. In our timeline, the Miocene grasslands triggered one of the great adaptive radiations in mammalian history. Horses evolved from small forest dwellers into the large, fast-running grazers we know today. Ruminants, cattle, deer, antelope, diversified explosively, their complex multi-chambered stomachs allowing them to extract nutrition from tough plant material that other mammals couldn't digest. Predators evolved to match. The ancestors of wolves and big cats became faster, more social, better adapted to hunting in open terrain. The modern African savanna, with its herds of wildebeest and zebra, its prides of lions and packs of wild dogs, is the culmination of 20 million years of evolution in grassland ecosystems. In our alternative timeline, the grasslands would have spread just as they did in our history. The climate patterns that created them had nothing to do with what animals were present. The difference is that it would have been dinosaurs, not mammals, facing the challenge of adapting to this new world. And the pressures would have been identical: eat grass or starve, run fast or die, see predators coming or become prey. The solutions, driven by the implacable logic of natural selection, would likely have been remarkably similar. Consider the ceratopsians, the horned dinosaurs that had dominated the herbivore niches of late Cretaceous North America. In the forests, they had been browsers, using their parrot-like beaks to crop vegetation and their shearing teeth to process it. But those teeth weren't designed for grass. They would have worn down quickly against the silica-laden tissues, leaving the animals unable to feed efficiently. The ceratopsians that survived in a grass-dominated world would have been those that evolved solutions to this problem. One possibility: the evolution of ever-growing teeth, similar to those of rodents and horses. The developmental pathways for continuous tooth growth exist in dinosaurs. We see hints of it in the dental batteries of Hadrosaurs, where teeth were constantly being replaced from below. A ceratopsian lineage that evolved truly hypsodont teeth would have been able to graze indefinitely, wearing down its teeth against the grass and simply growing more to replace them. Picture a descendant of Triceratops, 20 million years evolved from its Cretaceous ancestor. It's still recognizable as a ceratopsian. The basic body plan works too well to abandon, but the proportions have changed. The head is longer, lower to the ground, adapted for grazing rather than browsing. The beak is wider, more squared off, designed to crop grass in broad swaths like a living lawnmower. The frill has shrunk, no longer needed for display or thermoregulation in the same way. The energy instead invested in the massive jaw muscles needed to process tough vegetation. It moves in herds of hundreds across the Miocene prairies, a river of flesh and horn flowing across the landscape like wildebeest across the Serengeti. But grazing brings its own dangers. In a forest, you can hide from predators. On an open plain, you're visible from kilometers away. The only defenses are vigilance, numbers, and speed. The herding behavior of Miocene ceratopsians wouldn't have been optional. It would have been essential for survival. A lone grazer on an open plain is a dead grazer. A herd of 1,000 with hundreds of eyes scanning the horizon has a chance. The ornithomimosaurs, the ostrich dinosaurs of the Cretaceous, were already pre-adapted for grassland life in some ways. They were fast runners with long legs and light builds. They were probably omnivorous, able to exploit a variety of food sources. In a world of open plains, they might have become the ecological equivalents of antelope and gazelles, fast, alert, living in herds, relying on speed to escape predators. Imagine a Miocene ornithomimid, its legs even longer than its ancestors, its body streamlined for sustained running across flat terrain. Its neck is long enough to see over the grass, to spot danger approaching from any direction. It feeds on a mixture of grass seeds, insects, and small animals, an opportunistic diet that allows it to thrive in environments too harsh for specialists. When threatened, it can reach speeds of 60 kilometers per hour, fast enough to outrun any predator that relies on pure pursuit. It lives in groups of dozens, and when one individual spots danger and bolts, the others follow instantly, a wave of panic spreading through the herd faster than any predator can react. The Hadrosaurs present an interesting case. Their sophisticated dental batteries, those rows of hundreds of interlocking teeth, were already the most efficient plant processing machinery any dinosaur had ever evolved. In some ways, they were pre-adapted for grazing, capable of handling tough vegetation that would have defeated other herbivores. Perhaps, in our alternative timeline, the Hadrosaurs would have become the dominant grazers, their existing adaptations giving them a head start in the competition for grass. But there's another possibility, one that seems more likely given the rules of evolutionary competition. Perhaps no single lineage would have dominated. Perhaps the Miocene grasslands would have been partitioned among multiple dinosaur groups, each specializing in slightly different niches, just as the African savanna today is shared among wildebeest, zebra, buffalo, gazelle, and a dozen other species, each exploiting the grassland in its own way. The ecological theater had been rebuilt. The forest stage that had hosted the Mesozoic drama was being struck, replaced by an endless plain of waving grass under an open sky. New roles were available for any actors willing to learn new lines. The dinosaurs had spent 150 million years mastering forest life. Now they had perhaps 20 million years to master something entirely different. The question was, what would be hunting them? Because in a world of fast-running herds, the predators would have to change too. Tyrannosaurus rex was the apex predator of the late Cretaceous. 12 meters of muscle and bone, 6 tons of killing power, a bite force that could crush a car. It was built for one thing, taking down large prey through overwhelming force. In the forests of the Mesozoic, where ambush was possible and prey couldn't see you coming until it was too late, this strategy worked magnificently. T-Rex sat at the top of its food chain for millions of years, unchallenged, seemingly perfect. But perfection is always relative to environment. Change the environment, and perfection becomes obsolescence. The open grasslands of the Miocene would have been hostile territory for a classic tyrannosaur. In a forest, a 6-ton predator can hide behind trees, can approach within striking distance before its prey even knows it's there. On an open plain, there's no hiding a predator that stands 4 meters tall at the hip. Prey animals can see you coming from kilometers away. By the time you get close enough to attack, they're already running, and you, with your massive body and relatively short legs, cannot catch them. This doesn't mean the Tyrannosaur lineage would have gone extinct. Evolution doesn't give up on successful body plans that easily. But it does mean they would have had to change, and the direction of that change is predictable because we've seen it happen before with mammalian predators facing the same pressures. The tyrannosaurs of the Miocene grasslands would have become leaner. Natural selection would have favored individuals that were faster, lighter, more efficient runners. Over millions of years, the stocky body plan of T-Rex would have stretched and thinned, longer legs relative to body mass, a more horizontal posture for better balance at speed, perhaps a smaller head to reduce the weight carried at the front of the body. The result might have looked something like a scaled-up version of the earlier tyrannosaurs, creatures like Dilong or Guanlong, which were much more lightly built than their later descendants. But even a slimmed-down tyrannosaur would have faced a fundamental problem. The largest prey animals would have been herd animals, and hunting herd animals alone is dangerous and inefficient. A lone wolf can't bring down a healthy bison. A lone lion can't take a full-grown buffalo. The prey is too large, too dangerous, too surrounded by companions that might fight back. The solution, discovered independently by wolves and lions and African wild dogs, is cooperative hunting, working together in groups to isolate, exhaust, and overwhelm prey that no single individual could take. Here's where we encounter an interesting question about dinosaur behavior. We don't know for certain whether large theropods hunted in packs. There's some evidence, trackways that seem to show multiple individuals moving together, bone beds that contain many predators alongside their apparent prey, but it's ambiguous. Some paleontologists think tyrannosaurs were social hunters. Others think they were solitary, perhaps only coming together to scavenge or breed. In the absence of certainty, we have to reason from ecological principles. And ecological principles suggest that grassland tyrannosaurs would almost certainly have become pack hunters. Not because there's anything magical about grasslands, but because the prey they would have been hunting, large, dangerous, herd-dwelling dinosaurs, would have been almost impossible to take any other way. The selective pressure would have been intense. Individuals that could cooperate would have eaten. Individuals that couldn't would have starved. Over millions of years, that's enough pressure to reshape behavior, to build brains capable of coordination and communication, to create social structures that hadn't existed before. Picture a pack of Miocene tyrannosaurs, perhaps 6 or 8 individuals, moving across the grassland in the early morning light. They're smaller than their Cretaceous ancestors, maybe 7 meters long instead of 12, 3 tons instead of 6. But they're faster, more agile, working together with a coordination that T-Rex never needed. They've spotted a herd of grazing ceratopsians in the distance, and now they're spreading out, some circling wide to cut off escape routes, while others approach more directly to drive the herd toward the ambush. When they attack, it's not the overwhelming assault of a single giant predator, but a coordinated strike from multiple angles, each individual knowing its role, working together to bring down prey that none of them could kill alone. But the tyrannosaurs weren't the only theropod lineage adapting to the grasslands. The smaller predators, the dromaeosaurids, the troodontids, the other maniraptoran theropods, would have been evolving alongside them, filling different niches in the new ecosystem. In some ways, these smaller predators were better pre-adapted to grassland hunting than the tyrannosaurs were. They were already fast runners. Many of them already seem to have been social, hunting in groups based on the fossil evidence we have. They had grasping hands that could manipulate objects, forward-facing eyes that provided excellent depth perception, and relatively large brains for their body size. The grasslands would have rewarded all of these traits. The dromaeosaurids, the raptor dinosaurs popularized by Jurassic Park, would have been particularly well suited to pack hunting on the open plains. They were already pursuit predators, built for speed and agility. Their famous sickle claws were probably used to grip prey, while the jaws delivered killing bites, a technique that works better when multiple individuals can attack simultaneously. In our alternative timeline, the dromaeosaurid lineages might have diversified to fill roles similar to modern wild dogs and wolves, pack hunters that run down prey through persistence rather than ambush. Imagine a pack of Miocene dromaeosaurids, 2 meters long, covered in streaked feathers that break up their outlines against the grass. They hunt in groups of 20 or more, communicating through calls and body language, coordinating their movements across kilometers of open terrain. Their strategy is simple but effective. Identify a target, pursue it until it tires, take turns keeping pressure on while others rest. It's the same strategy used by African wild dogs today, and it's devastatingly effective against prey that relies on speed for survival. No animal can run at maximum speed forever. Eventually, exhaustion wins. The troodontids represent perhaps the most intriguing possibility. These were the intellectuals of the dinosaur world. Small, lightly built theropods with the largest brain-to-body size ratio of any known dinosaur. We'll explore their potential in more detail in the next chapter, but they would have been formidable grassland predators in their own right, probably hunting smaller prey that the larger predators ignored, perhaps developing more sophisticated social structures than any of their relatives. The Miocene grasslands, in our alternative timeline, would have been a killing ground patrolled by predators at every scale. At the top, packs of slimmed-down Tyrannosaurs, still the largest land predators on Earth, but fundamentally transformed by 50 million years of adaptation to new conditions. In the middle, packs of dromaeosaurids, running down prey through sheer endurance. At the bottom, troodontids and other small theropods, hunting everything from rodent-sized mammals to insects to each other. The age of the lone giant was ending. The solitary tyrannosaur, killing through overwhelming individual power, was giving way to something new. Predators that succeeded through cooperation, coordination, perhaps even the beginnings of something we might call strategy. In a world of open plains and vigilant herds, brains were becoming as important as brawn. And that raises a question that paleontologists have debated for decades. Given enough time, another 50 million years, say, could dinosaurs have evolved true intelligence? Could they have developed minds capable of understanding the world, of planning for the future, of asking questions about their own existence? The answer is more complicated than you might think. In 1982, a Canadian paleontologist named Dale Russell published a thought experiment that would become one of the most famous and most controversial pieces of speculative paleontology ever written. Russell had been studying Troodon, a small theropod dinosaur from the late Cretaceous, known for having an unusually large brain relative to its body size. Looking at the trend of increasing brain size in this lineage, Russell asked a simple question. What if the dinosaurs hadn't gone extinct? What might Troodon's descendants have become after another 66 million years of evolution? His answer was the Dinosauroid, a hypothetical creature that stood upright on 2 legs, had manipulative hands with opposable digits, and possessed a large, rounded brain case capable of housing human-level intelligence. Russell even commissioned a sculpture of his Dinosauroid, and the result was strikingly humanoid. 2 forward-facing eyes, a vertical posture, a body plan that looked more like a grey alien than a dinosaur. The implication was clear. Given enough time, dinosaurs might have evolved intelligence comparable to our own. we might have had competition. The Dinosauroid hypothesis captured the public imagination, but it was criticized almost immediately by other scientists, and the criticism has only intensified in the decades since. The problem isn't the idea that dinosaurs might have become more intelligent. That's reasonable speculation, supported by the evidence we have. The problem is the assumption that intelligence inevitably leads to a humanoid body plan. Russell's reasoning went something like this. Intelligence requires a large brain. A large brain requires an upright posture to balance it on the spine. An upright posture requires the forelimbs to be free from locomotion. Free forelimbs naturally evolve into manipulative hands. Therefore, any intelligent creature will eventually look more or less like a human. It's a seductive argument, but it's almost certainly wrong. Consider the most intelligent non-human animals alive today. Crows and parrots have demonstrated cognitive abilities that rival great apes. They use tools, solve complex problems, recognize themselves in mirrors, and appear to understand concepts like cause and effect. Yet they look nothing like humans. They're birds with wings and beaks and bodies shaped by 150 million years of avian evolution. Their intelligence evolved within the constraints of a very non-humanoid body plan, and those constraints didn't prevent them from becoming remarkably smart. Or consider octopuses, which can solve puzzles, use tools, and appear to possess something like individual personalities. An octopus is about as far from a humanoid body plan as you can get. 8 arms, no skeleton, a distributed nervous system with neurons in each tentacle. Yet they're among the most intelligent invertebrates on Earth, perhaps among the most intelligent animals, period. The lesson is that intelligence is not a destination that evolution is trying to reach. It's a tool like claws or wings or venom that evolves when the selective pressures favor it. And it can evolve in bodies of almost any shape, because intelligence is ultimately about information processing, not about having hands or standing upright. So what would intelligent dinosaurs actually have looked like? Probably like dinosaurs. The troodontids of our alternative timeline, after 66 million years of additional evolution, would still have been recognizable as theropod dinosaurs. They would have retained the basic body plan that had served their ancestors so well. Bipedal locomotion, a horizontal posture balanced by a long tail, grasping forelimbs, a head full of sharp teeth. What would have changed was inside that head. The troodontid brain was already large for a dinosaur. The encephalization quotient, a measure of brain size relative to body size, was higher in Troodon than in any other known dinosaur. If the selective pressures we discussed in the previous chapter continued to favor cognitive ability, if pack hunting demanded better coordination, if grassland life required better spatial memory, if complex social structures required recognizing individuals and remembering relationships, then the troodontid brain might have continued to expand. How far? That's impossible to say with certainty. But we can look at what happened with birds, the only dinosaur lineage that survived the extinction, for clues. Crows and parrots have brain-to-body ratios comparable to great apes, and they evolved that level of encephalization in roughly the same 66 million years that we're imagining for our alternative troodontids. It's not unreasonable to suppose that a lineage starting with Troodon's already impressive brain might have reached similar levels. Picture a troodontid of the late Miocene, perhaps 10 million years ago in our alternative timeline. It's about 2 meters long from snout to tail tip, covered in feathers that range from grey on the back to white on the belly, camouflage for the open grasslands where it hunts. Its eyes are large and forward-facing, providing excellent binocular vision. Its hands retain 3 clawed fingers, capable of grasping and manipulating objects with a precision its Cretaceous ancestors couldn't have managed. And its brain, housed in a skull that bulges noticeably at the back, is the largest of any land animal on Earth in proportion to its body size. This creature is smart, not human smart, we'll get to why in a moment, but smart in ways that matter for survival. It hunts in packs of 10 to 20 individuals, and the coordination of those hunts is remarkable. Flanking maneuvers, diversionary tactics, even what appears to be deliberate deception, with some individuals feigning injury to lure prey into ambushes. It uses simple tools, sticks to probe burrows for hidden prey, rocks to crack open hard-shelled food items. It has a complex vocal repertoire, dozens of distinct calls that communicate information about predators, food sources, and social status. Young troodontids learn from their elders, watching and imitating behaviors rather than relying purely on instinct. In many ways, this creature would have occupied an ecological niche similar to modern wolves or early hominids, a social predator whose success depends more on brains than on brawn, more on cooperation than on individual strength. It would have been formidable, adaptable, capable of thriving in environments across the globe, but it would not have built cities. It would not have developed writing or mathematics or philosophy. It would not have asked questions about the stars or wondered about its place in the universe. Why not? Because human-level intelligence isn't just about having a big brain. It's about a very specific set of circumstances that, as far as we can tell, occurred exactly once in the history of life on Earth. Human intelligence evolved in primates, a lineage that had already spent tens of millions of years developing complex social structures, manipulative hands adapted for grasping branches, and brains adapted for navigating three-dimensional environments. Then, our ancestors were forced out of the trees and onto the African savanna, where they faced new selective pressures: the need to find food in a challenging environment, the need to cooperate in groups, the need to communicate complex information about resources and dangers. Our brains expanded dramatically over just a few million years, driven by a feedback loop between social complexity and cognitive ability. This sequence of events was contingent on countless factors, each one necessary but not sufficient on its own. Primates reached Africa, but the 3 times they reached North America, none of those lineages evolved large brains. Grasslands appeared on every continent, but only in Africa did they produce a species capable of abstract thought. Intelligence of some kind might be common in the universe, but intelligence like ours, capable of technology and science and philosophy, might be vanishingly rare. Our alternative troodontids would have been intelligent, perhaps as intelligent as crows or dolphins or chimpanzees. They might have used tools, formed complex societies, passed knowledge from generation to generation. But the spark that lifted our ancestors from clever ape to wondering human, that spark might never have occurred in a dinosaur lineage, no matter how many millions of years it had to evolve. The dinosaurs could have produced creatures that thought, but not creatures that wondered why they thought. And yet, there's something almost comforting in that limitation, because it means that in our alternative timeline, the Earth would have remained wild, beautiful and brutal, and utterly indifferent to meaning. A planet of animals doing what animals do, without anyone there to call it magnificent or terrible, or ask whether it had any point at all. The dinosaurs would have ruled for 230 million years, unchallenged, unmarked by any species capable of recording their existence. In that world, there would be no one to miss us, because there would be no one to know we might have been. 2.5 million years ago, the Earth crossed a threshold. The long cooling that had begun in the Oligocene, that had transformed tropical forests into temperate woodlands and woodlands into grasslands, finally reached its logical conclusion. Ice sheets began to form in the northern hemisphere, not just on isolated mountain peaks, but spreading across entire continents, burying Scandinavia and Canada under kilometers of frozen water. The Pleistocene had begun, and with it came a climate regime unlike anything the planet had experienced in over 250 million years. The ice didn't advance once and stay. Instead, it pulsed, advancing during glacial periods that lasted roughly 100,000 years, retreating during interglacials that lasted 10,000 to 20,000 years. Over the course of the Pleistocene, there were more than 20 of these cycles, each one reshaping the planet's geography, pushing ecosystems towards the equator and then allowing them to rebound, creating and destroying land bridges, forcing species to adapt or die. In our timeline, this era produced the iconic megafauna of the Ice Age: woolly mammoths with their shaggy coats and curved tusks, woolly rhinoceroses built like furry tanks, cave bears that stood 3 meters tall on their hind legs, giant ground sloths the size of elephants. These animals evolved specifically for glacial conditions: massive bodies to retain heat, thick fur or fat layers for insulation, the ability to survive on sparse vegetation during the long winters. They were the defining creatures of their age. In our alternative timeline, there would have been no mammoths, no woolly rhinos, no giant sloths. Those niches, large, cold-adapted herbivores, would have been filled by something else entirely. They would have been filled by dinosaurs. The question is whether dinosaurs could have survived the ice ages at all. This is their greatest test, the challenge that would push them further from their evolutionary comfort zone than anything they had faced before. For 200 million years, dinosaurs had thrived in a greenhouse world, warm, wet, forested. The grasslands of the Miocene had been a significant change, but temperatures had still been mild by Pleistocene standards. Now they would face winters where temperatures dropped to -40 degrees Celsius, where snow covered the ground for 8 months of the year, where food became desperately scarce and survival required either migration or the ability to endure months of privation. Could they do it? We have reasons to think they could. Remember the Prince Creek Formation in Alaska, where dinosaurs lived year-round above the Arctic Circle during the Cretaceous. Remember that feathers evolved specifically for insulation, that many dinosaur lineages were already equipped with nature's most effective cold-weather clothing. Remember that birds, living dinosaurs, thrive in some of the coldest environments on Earth today, from penguins in Antarctica to snowy owls in the Arctic tundra. The adaptations required for Pleistocene survival would have been significant, but they wouldn't have required dinosaurs to become something fundamentally different. They would have required them to become more of what they already were. Consider the ceratopsians, those horned herbivores that had already adapted to grassland life in the Miocene. A Pleistocene ceratopsian would have been a magnificent creature. Imagine something like a Triceratops, but transformed by 60 million years of adaptation to increasingly harsh conditions. Its body would have been massive, perhaps 8 or 9 meters long, bulked up with fat reserves that could sustain it through the lean winter months. Its frill, once used primarily for display and thermoregulation, would have shrunk and thickened, becoming more functional, less ornamental. And covering its entire body, from the tip of its nose to the end of its tail, would have been a dense coat of feathery integument. Not the elaborate plumage of a tropical bird, but the thick, insulating down of an animal built for survival in extreme cold. Picture this creature on a Siberian steppe during an interglacial period, moving in a herd of hundreds across a landscape of grass and low shrubs. It looks almost mammalian at first glance, that shaggy coat, that massive bulk, but the silhouette is unmistakably dinosaurian. The four-legged stance, the beaked face, the horns protruding from the brow. It feeds on tough, low-growing vegetation, its dental battery grinding plant material with an efficiency that no mammal could match. When winter comes, it will migrate south, following the retreating warmth, returning north only when the snows melt and new growth appears. The Hadrosaurs would have faced similar pressures and likely developed similar solutions. Their sophisticated feeding apparatus, those dental batteries with hundreds of interlocking teeth, would have served them well on a diet of tough Arctic vegetation. Their bipedal ancestors had long since given way to animals that walked on all fours most of the time, their bodies low and wide and heavily insulated. In the winter months, they would have congregated in valleys that offered some protection from the wind, huddling together for warmth the way musk oxen do today. The predators would have adapted too. A Pleistocene Tyrannosaur, descended from the pack-hunting lineages of the Miocene, would have been a creature of nightmares, smaller than its Cretaceous ancestors, perhaps only 5 meters long, but covered in a thick coat of white and grey feathers that rendered it nearly invisible against a snowy backdrop. It would have hunted in coordinated packs, taking down prey many times its individual size through teamwork and persistence. In the depths of winter, when prey was scarce, it might have been able to slow its metabolism and enter a torpor-like state, surviving on stored fat until spring brought new opportunities. But not all dinosaurs would have adapted to the cold. Some lineages would have retreated to the tropics, surviving in equatorial refugia where temperatures remained mild even during the glacial maxima. South America, isolated by the Central American Seaway for much of the Cenozoic, might have become a repository of ancient forms, descendants of Cretaceous lineages that had never needed to adapt to cold or grasslands, preserved in tropical forests like living fossils. Southeast Asia and Central Africa would have served similar roles, islands of warmth in an increasingly frigid world. The result would have been a planet divided into climatic zones more sharply than at any time since the dinosaurs first appeared. In the tropics, something like the old Mesozoic world might have persisted, warm, forested, populated by dinosaurs that would have looked familiar to a visitor from the Cretaceous. In the temperate and polar regions, something new would have emerged. Dinosaurs transformed by 60 million years of adaptation to conditions their ancestors never imagined, as different from Tyrannosaurus and Triceratops as mammoths were from their tropical elephant ancestors. The Ice Ages would have been a crucible, testing the dinosaurs more severely than anything in their previous 200 million year history. Some lineages would have failed the test, going extinct as the climate pushed them beyond their limits. Others would have passed it, emerging from the glacial cycles hardened and adapted, ready for whatever came next. And what came next, in our timeline, was us. A species of clever ape that walked out of Africa and spread across the globe, hunting megafauna to extinction, reshaping ecosystems, eventually building civilizations that could ponder the deep history of their planet. In our alternative timeline, that species would never have existed. The conditions that produced human intelligence, the specific sequence of events in African primate evolution, would have played out differently, or not at all. The Pleistocene would have ended without anyone there to name it. But the glacial cycles themselves would have continued, advancing and retreating on their 100,000-year rhythm. And with each cycle, the dinosaurs of the frozen world would have migrated and adapted and survived, as they had survived everything else the planet had thrown at them. After 230 million years, they had become the ultimate survivors. The ice was just one more challenge, and they had met it. There's a rule in biology called Bergmann's rule, and it's remarkably simple. Within a species or lineage, individuals tend to be larger in colder climates. The reason is thermodynamics. A larger body has a smaller surface area to volume ratio, which means it loses heat more slowly. In a cold environment, being big is an advantage. You can retain your body heat more efficiently. You can store more fat to survive lean times. You can simply endure conditions that would kill a smaller animal. Bergmann's rule shaped the megafauna of our Pleistocene. Woolly mammoths were larger than their tropical elephant relatives. Cave bears dwarfed modern brown bears. The giant deer of Ireland carried antlers spanning 3.5 meters, absurdly large, almost comically oversized, but supported by a body massive enough to carry them. Cold-made giants. In our alternative timeline, the same rule would have applied, and it would have produced giants of a very different kind. The ceratopsians of the Pleistocene steppes would have been the largest members of their lineage since the days of the Cretaceous, perhaps larger. A full-grown adult might have measured 10 meters from beak to tail, standing 2.5 meters at the shoulder, weighing 8 or 9 tons. Its horns would have been shorter than those of Triceratops, less elaborate, more functional. Weapons for defense against predators and competition for mates rather than the ornate display structures of its ancestors. Its body would have been barrel-shaped, packed with the fat reserves and fermentation chambers needed to process enormous quantities of low-quality vegetation during the brief Arctic summer and survive the long winter on stored energy. These animals would have moved in herds that darkened the horizon. Not dozens or hundreds, but thousands. Rivers of flesh flowing across the mammoth steppe, following the seasonal pulse of vegetation growth. In summer, they would have pushed north into the high Arctic, grazing on the explosion of plant life that the endless daylight produced. In winter, they would have retreated south, congregating in valleys where snow was less deep and some vegetation remained accessible. The scale of these migrations would have been staggering. Millions of animals moving in synchrony across thousands of kilometers, one of the great wildlife spectacles of the planet. The hadrosaurs would have shared these grasslands, their populations perhaps even larger than the ceratopsians. Their dental batteries gave them an edge in processing the toughest vegetation, and their ability to walk on either 2 or 4 legs might have proved useful in deep snow, where they could rear up to browse on shrubs and low trees when ground-level vegetation was buried. Picture a Pleistocene hadrosaur 7 meters long, its body covered in a dense coat of filamentous feathers that trapped warm air against the skin, its duck-like bill adapted for cropping vegetation close to the frozen ground. It moves through a snowstorm in a herd of several hundred, the animals pressed close together for warmth, their breath forming clouds in the frigid air. But the northern steppes were only part of the story. The Pleistocene world was a patchwork of different environments, and each would have produced its own characteristic dinosaur fauna. Beringia, the land bridge that connected Asia and North America during glacial periods, would have been a highway for dinosaur migration, just as it was for mammoths and humans in our timeline. Species that evolved in Asia would have crossed to the Americas and vice versa, creating a shared fauna across the northern continents. The Tyrannosaurs of Siberia would have been cousins to the Tyrannosaurs of Alaska, separated by only a few thousand kilometers of continuous habitat. The Ceratopsians of Mongolia would have mingled with the Ceratopsians of Wyoming. It would have been a single great ecosystem stretching from France to Florida, united by the cold. Further south, the tropical refugia would have preserved something very different. In the Amazon basin, in the Congo, in Southeast Asia, fragments of the old forest world would have persisted through the glacial cycles, warmed by their equatorial location even as ice sheets buried the higher latitudes. Here, you might have found dinosaurs that looked almost Cretaceous, sauropods still browsing in the canopy, small theropods hunting in the understory, a world that time had almost forgotten. These refugia would have been islands of biodiversity, preserving lineages that had gone extinct elsewhere, serving as sources for recolonization when the ice retreated. The predators of the frozen world would have been as impressive as their prey. The pack-hunting tyrannosaurs we imagined in earlier chapters would have reached their peak in the Pleistocene, their social structures refined by millions of years of evolution, their hunting strategies honed to perfection. A pack of Pleistocene tyrannosaurs taking down a full-grown ceratopsian would have been a spectacle of coordinated violence, some individuals driving the prey, others cutting off escape routes, still others waiting in ambush, the whole group working together with a precision that spoke to generations of learned behavior passed from parents to offspring. Smaller predators would have filled other niches. The dromaeosaurids, those feathered pursuit hunters, would have been common on the open steppes, hunting in packs that could number in the dozens, taking down mid-sized prey through sheer persistence. Solitary hunters might have stalked the forest edges, ambushing prey from cover, and the troodontids, those large-brained, tool-using hunters we imagined in Chapter 9, might have become the most versatile predators of all, capable of taking a wide range of prey through a combination of intelligence, cooperation, and adaptability. The seas would have had their own Pleistocene fauna. The mosasaur and plesiosaur lineages, by now diversified into dozens of species filling niches from coastal fish-eaters to open-ocean giants, would have navigated the same cold waters that supported whales and seals in our timeline. Some might have developed thick layers of blubber for insulation, converging on the body plans of marine mammals. Others might have become seasonal migrants, following prey species between tropical and temperate waters. The largest, descendants of the great marine reptiles of the Mesozoic, might have rivaled the great whales in size, filter feeding on krill and small fish in the productive polar seas. The glacial cycles would have created a rhythm of expansion and contraction, of extinction and speciation, of adaptation and readaptation. Each advance of the ice would have pushed species toward the equator, fragmenting populations and creating opportunities for divergence. Each retreat would have allowed recolonization of newly available habitat, bringing previously separated populations back into contact. Over 2 million years, this pulse would have driven evolution at an accelerated pace, producing diversity and specialization at rates rarely seen in Earth's history. The Ice Ages didn't destroy the dinosaurs of our alternative timeline. They transformed them. They pushed them to evolve solutions to problems their ancestors had never faced, to develop bodies and behaviors suited to conditions that would have been unimaginable in the warm Cretaceous world where their lineage began. The giants of the frozen world were the culmination of 230 million years of dinosaur evolution, not the end of a story, but the latest chapter in an ongoing saga. And then the current interglacial began. The ice retreated, temperatures rose. The mammoth steppe gave way to forest and tundra, and the world that emerged, the world of the present day, would have been shaped by 66 million years of history that never happened in our timeline. A world still ruled by dinosaurs. Stand on a hilltop in our alternative present and look out across the landscape. The geography is familiar, the same mountains, the same rivers, the same coastlines that you would recognize from our world. Continental drift operates on timescales of millions of years, and 66 million years isn't enough to rearrange the continents significantly. Africa still presses against Europe, creating the Mediterranean. India has long since collided with Asia, raising the Himalayas. The Americas stretch from pole to pole, connected by the narrow isthmus of Central America. The map is the same map you learned in school, but the animals on that map are completely different. Let's take a tour of this alternative Earth, continent by continent, ecosystem by ecosystem. Let's see what 230 million years of uninterrupted dinosaur evolution has produced. Start in Africa, on the savannas of East Africa, where, in our timeline, you would find the greatest concentration of large mammals on Earth. The geography that created the Serengeti exists in our alternative timeline too. The same volcanic soils, the same seasonal rainfall patterns, the same endless grasslands stretching to the horizon. But instead of wildebeest and zebra, you would see herds of ceratopsians, their horned heads bobbing as they graze. their bodies covered in sparse feathery integument adapted to the tropical heat. Some species would be massive, the size of elephants, filling the megaherbivore niche. Others would be smaller, faster, living in larger herds that rely on vigilance and numbers for protection. The predators would be familiar in function, if not in form. Packs of medium-sized theropods, descendants of the Tyrannosaur or Dromaeosaurid lineages, would patrol the edges of the herds, looking for the weak, the young, the isolated. Their hunting strategies would be sophisticated, honed by millions of years of coevolution with their prey. Some would be pursuit hunters, running down their targets over kilometers like African wild dogs. Others would be ambush predators, lying in wait in the tall grass, striking with explosive speed when prey wandered too close. The skies above the savanna would be filled with pterosaurs, not the giants of the Cretaceous, but smaller species adapted to the modern world, filling niches occupied by vultures and eagles in our timeline. Some would be scavengers, circling above kills and descending to clean the bones. Others would be active hunters, diving on small prey with the precision of falcons. And birds would be there too, of course, the one dinosaur lineage that survived the real extinction, now sharing the sky with their pterosaur cousins in a world where both groups had the chance to diversify. Cross the Atlantic to South America, and you would find something different. South America spent much of the Cenozoic isolated from other continents, and in our timeline, that isolation produced unique fauna, giant ground sloths, terror birds, strange hoofed mammals found nowhere else. In our alternative timeline, the isolation would have produced unique dinosaurs instead. Perhaps sauropods would have persisted here, their long-necked forms still browsing in the forests of the Amazon basin, an ancient body plan preserved in a continental refugium. Perhaps entirely new dinosaur lineages would have evolved, forms unlike anything seen on other continents, the product of tens of millions of years of independent evolution. Australia would be stranger still. In our timeline, Australia's isolation produced marsupials and monotremes, mammals that evolved independently of their placental relatives on other continents. In our alternative timeline, Australia would have been isolated with whatever dinosaur fauna happened to be present when it separated from Antarctica, roughly 45 million years ago. Those dinosaurs would have evolved in complete isolation ever since, producing forms as unique and unexpected as the platypus and kangaroo are to us. Without knowing exactly what dinosaurs were present at the moment of separation, we can't say what Australian dinosaurs would look like, only that they would be different from dinosaurs anywhere else on Earth. The northern continents, Eurasia and North America, would be dominated by the grassland fauna we've been tracing throughout this documentary. Ceratopsians and hadrosaurs grazing in vast herds, Tyrannosaurs and Dromaeosaurids hunting in coordinated packs, Troodontids using tools and living in complex social groups. The fauna would vary with latitude and climate, tropical forests in the south giving way to temperate woodlands, then grasslands, then tundra in the far north, but the basic cast of characters would be recognizable across the entire supercontinent. The oceans would be the realm of the marine reptiles. Mosasaurs and plesiosaurs, by now diversified into hundreds of species, would fill every marine niche from coastal waters to the open ocean. Some would be small, agile fish eaters, darting through kelp forests and coral reefs. Others would be massive filter feeders, cruising the productive polar waters with mouths agape, straining krill and small fish from the sea, the way baleen whales do in our timeline. The largest might rival the blue whale in size, 30 meters long, 150 tons, the biggest animals ever to live, their bodies supported by the buoyancy of the water that would crush them if they ever came ashore. What you would not see anywhere on this alternative Earth is a human. No cities on the horizon, no roads cutting across the grasslands, no ships on the oceans or aircraft in the skies, no farms, no fences, no domesticated animals following human commands. The world would be wild in a way that our world hasn't been wild for 10,000 years. Perhaps in a way that our world was never wild, because even before agriculture, humans were reshaping ecosystems through hunting and fire. This absence would change everything about how the planet worked. Without humans to hunt them, the megafauna would be far more abundant than in our timeline. The ceratopsian herds of Africa might number in the tens of millions, their combined biomass exceeding anything we've ever seen in the mammalian world. Without humans to fragment habitats, ecosystems would be continuous across entire continents, allowing migrations and gene flow on scales impossible in our developed world. Without humans to drive species extinct, the biodiversity of the planet would be higher, not just because the dinosaurs would be there, but because all the cascading extinctions that humans caused in our timeline would never have happened. And the planet's chemistry would be different too. No fossil fuels burned, no carbon dioxide pumped into the atmosphere, no global warming threatening to destabilize the climate. The alternative Earth of 2026 would still be in the grip of the Pleistocene Ice Age cycle, heading toward another glacial maximum in a few thousand years, its climate controlled by orbital mechanics and volcanic activity rather than industrial emissions. The dinosaurs would face that coming ice age the way they faced every previous one, through migration, adaptation, and the slow grind of natural selection. Looking at this world, you might ask, is it better than ours? Is a world ruled by dinosaurs somehow superior to a world ruled by humans? The question doesn't really have an answer. Better for whom? The dinosaurs would presumably prefer their world, if they were capable of preference. The mammals that never got their chance to dominate might disagree. The planet itself doesn't care. It's just a ball of rock and water and air, indifferent to what kinds of organisms happen to be crawling across its surface. But there's something to be said for a world that has been stable for 230 million years. A world where no single species has reshaped the entire biosphere to suit its needs. A world where evolution proceeds at its natural pace, driven by climate and competition and chance, rather than the deliberate choices of a technological civilization. There's a kind of purity to such a world, even if there's no one there to appreciate it. The dinosaurs didn't choose to rule the Earth. They simply evolved to fit the conditions they found, and then they kept evolving as those conditions changed. They survived asteroid impacts and volcanic eruptions, ice ages and greenhouse spikes, the rise of flowering plants and the spread of grasslands. They were the ultimate generalists, the great survivors, the lineage that found a way to persist through everything the planet threw at them. In our timeline, a rock from space ended their reign. In our alternative timeline, nothing ever did. The world today belongs to them, as it has for 230 million years, and there's no one to say otherwise. We've spent this entire documentary talking about dinosaurs, what they would have become, how they would have adapted, what forms they would have evolved to fill the niches of the modern world. But there's a question we haven't addressed directly, a question that might have been nagging at you since the beginning. What happened to the mammals? In our timeline, the extinction of the dinosaurs was the mammals' great opportunity. For 150 million years, they had lived in the shadows, small, mostly nocturnal, relegated to ecological niches that the dinosaurs didn't want or couldn't fill. Then the asteroid hit, the dinosaurs died, and suddenly the world was empty. The mammals exploded into that emptiness, diversifying into every available niche, evolving into forms that ranged from tiny shrews to giant whales, from burrowing moles to soaring bats. Within 10 million years of the extinction, they had conquered the planet. In our alternative timeline, that opportunity never came. The dinosaurs survived, and the mammals remained in the shadows. But shadows aren't nothing. The mammals wouldn't have gone extinct. They would simply have remained what they had been for the previous 150 million years. Small, secretive, successful in their own limited way. And over 66 million years of continued evolution, they would have diversified within those constraints, filling every niche that the dinosaurs couldn't reach. The night would have belonged to them. Dinosaurs, for all their diversity, were almost certainly diurnal, active during the day, sleeping at night. The evidence suggests that early mammals evolved their warm-blooded metabolism and enhanced senses specifically to exploit the nocturnal niche, hunting insects and avoiding dinosaur predators in the darkness. In our alternative timeline, that niche would have remained theirs. The forests of the modern world would come alive after sunset with small, furry creatures hunting and foraging and living their entire lives in the hours between dusk and dawn. The underground would have belonged to them too. Burrowing is a strategy that favors small bodies. The energy required to dig increases rapidly with size, and mammals had been burrowing since the Mesozoic. In our alternative timeline, an entire ecosystem might exist beneath the feet of the dinosaurs, networks of tunnels and chambers occupied by mammal species that rarely or never venture to the surface. These subterranean mammals might have evolved remarkable adaptations, enhanced hearing to navigate in darkness, sensitive whiskers to feel their way through tunnels, reduced eyes, or even complete blindness. They would be invisible to the dinosaurs walking above them, a hidden world that the rulers of the surface would never even know existed. The treetops would have offered another refuge. Small mammals can climb where large dinosaurs cannot, and the high canopy of a tropical forest might have been essentially dinosaur-free, a world of branches and leaves accessible only to creatures light enough to walk on thin limbs. Here, in our alternative timeline, primate-like mammals might have evolved, grasping hands and forward-facing eyes, adapted for life in the three-dimensional maze of the canopy. They wouldn't be primates in the technical sense. That lineage might have evolved very differently, but they would fill similar niches, perhaps developing similar adaptations through convergent evolution. Could intelligence have evolved among these shadowy mammals? It's possible, though perhaps unlikely. The pressures that drove the evolution of human intelligence were specific. Life on the African savanna, the need to find food across large territories, the advantages of cooperation and tool use. None of those pressures would have applied to small nocturnal mammals hiding from dinosaurs. They might have evolved intelligence comparable to modern raccoons or rats, clever, adaptable, capable of solving problems. But the spark that created human-level consciousness might never have been struck. But here's an interesting twist. The mammals might have found success in a realm that the dinosaurs never fully conquered: the open ocean. In our timeline, whales and dolphins evolved from land-dwelling mammals that returned to the sea roughly 50 million years ago. They became the dominant large predators and filter feeders of the modern ocean, filling niches that had been empty since the extinction of the marine reptiles. In our alternative timeline, those niches would have been occupied by mosasaurs and plesiosaurs, but perhaps not all of them. The mosasaurs and plesiosaurs were air breathers, tied to the surface, limited in how deep they could dive and how long they could stay submerged. A mammal lineage that evolved for deep diving, developing the extreme breath-holding capacity and pressure tolerance that modern whales possess, might have been able to exploit resources that the marine reptiles couldn't reach. The deep sea, that vast realm of darkness below the sunlit surface, might have become a mammalian domain. Picture a creature in the dark waters of the alternative present, a mammal, warm-blooded, descended from some small ancestor that took to the sea while the dinosaurs still ruled the land. It's the size of a dolphin, perhaps, streamlined for swimming. its limbs transformed into flippers, its body insulated by a thick layer of blubber. It hunts in the deep scattering layer, that zone of concentrated life hundreds of meters below the surface, diving for 30 minutes or more on a single breath, using echolocation to find prey in the absolute darkness. Above it, mosasaurs patrol the sunlit waters. But down here, in the cold and the dark, the mammal is alone, master of a realm that the reptiles never learned to exploit. This is speculation, of course. We can't know what mammals would have evolved in a world where dinosaurs survived, but the point is that they would have evolved something. Life finds a way, as the saying goes, not through some mystical force, but through the simple mathematics of variation and selection. Any niche that exists will eventually be filled by something. The mammals would have found niches that the dinosaurs couldn't fill, and they would have diversified to exploit them. They wouldn't have inherited the Earth. That prize would have remained with the dinosaurs as it had for 230 million years. But they would have persisted, adapted, survived. They would have become masters of the margins, lords of the shadows, a parallel dynasty thriving in all the spaces that the reptilian rulers overlooked. The mammals never went extinct in our alternative timeline. They just never got their chance to shine. And perhaps in the dark forests and deep oceans of that alternative Earth, they're still waiting. Here's a strange thought to sit with. If you're listening to this, if you're hearing these words and understanding them, then the asteroid hit. That's the paradox at the heart of this entire thought experiment. The very act of imagining a world where dinosaurs survived requires a mind capable of imagination. And that mind, your mind, exists only because the dinosaurs died. Human intelligence is not some inevitable endpoint of evolution, some destination that life was always heading toward. It's a contingency, an accident, the improbable result of a very specific sequence of events that began with a rock from space striking the Yucatan Peninsula 66 million years ago. If the asteroid had missed, there would be no one to wonder what might have been. This is not to say that intelligence couldn't have evolved in our alternative timeline. We've discussed the troodontids, those large-brained theropods that might have developed cognitive abilities comparable to modern crows or dolphins. We've speculated about the social hunters of the Miocene, the pack-dwelling predators that might have evolved increasingly sophisticated communication and cooperation. Intelligence of some kind would almost certainly have appeared somewhere in the dinosaur family tree. It's too useful an adaptation not to evolve when conditions favor it. But intelligence like ours, consciousness that can contemplate its own existence, ask questions about the nature of reality, feel wonder at the vastness of the cosmos, that's something else entirely. Human consciousness emerged from a very particular set of circumstances. Our ancestors were primates, a lineage that had spent tens of millions of years developing complex social structures, manipulative hands, and brains adapted for navigating three-dimensional environments. Then climate change forced them out of the forests and onto the African savanna, where they faced new selective pressures that favored cooperation, communication, and the ability to plan for the future. Our brains expanded dramatically over just a few million years, driven by a feedback loop between social complexity and cognitive ability that seems to have occurred nowhere else in the history of life on Earth. Every step of that journey was contingent. If the primates had never reached Africa, if the climate hadn't changed when it did, if our ancestors had adapted to the savanna in some other way, the outcome might have been completely different. Intelligence might have evolved, but not the kind of intelligence that builds telescopes and writes documentaries and wonders about alternative histories. In our alternative timeline, none of those contingencies would have played out the same way. The primates might not have existed at all, or might have remained small tree dwellers, never descending to the ground. The savanna might have been dominated by dinosaurs, leaving no ecological space for an upstart ape to develop new survival strategies. The specific combination of pressures that produced human consciousness would never have come together, and so there would be no one to ask the question that you're asking right now. What if things had been different? But here's the thing, and this is the thought I want to leave you with. The absence of human-style intelligence doesn't make the alternative world lesser. It doesn't make it worse, or emptier, or less meaningful. It makes it different. And different is not the same as inferior. The alternative Earth we've been imagining throughout this documentary would be a world of staggering beauty and complexity. Herds of ceratopsians flowing across grasslands like living rivers, packs of feathered predators hunting with coordination and intelligence, marine reptiles cruising through oceans that have never known a fishing net or an oil spill, Pterosaurs soaring on thermal currents above mountains that have never been climbed. Life in all its diversity and struggle and improbable persistence playing out on a stage that has remained essentially unchanged for 230 million years. That world would not need us to appreciate it. It would not need a conscious observer to give it meaning. It would simply be, as our world simply is, a planet covered with living things, each one the product of billions of years of evolution, each one perfectly adapted to its niche, each one part of an interconnected web of relationships more complex than any mind could fully comprehend. We tend to think of consciousness as the point of evolution, the goal toward which life has been striving since the first cell divided in some ancient ocean. But that's our bias talking, the natural tendency of any thinking being to assume that thinking is what matters most. Evolution doesn't have a point, it doesn't have a goal, it's simply a process, variation, selection, inheritance, playing out over deep time, producing whatever forms happen to survive and reproduce in whatever conditions happen to exist. Dinosaurs weren't failures because they didn't evolve human-level intelligence. They were successes, spectacular, unprecedented successes, because they dominated the planet for 165 million years and left descendants that still fill the skies today. If they had survived the asteroid, they would have continued to be successes, adapting to whatever challenges the planet threw at them, diversifying into whatever niches became available, living and dying and evolving without ever once wondering why. And maybe there's something to be said for that, for a world that simply exists without the burden of consciousness, without the weight of meaning, without the endless human need to understand and explain and justify. A world where life just lives without asking what it's all for. The asteroid hit, the dinosaurs died, and here you are, 66 million years later, listening to a story about a world that never was. But as you drift towards sleep, maybe you can imagine it. The warm darkness of a Mesozoic night, the sounds of creatures moving through the forest, the stars wheeling overhead, the same stars that shine in our sky, the same moon, the same slow dance of the cosmos that doesn't care what walks below it. In that world, something is sleeping too. Some descendant of the dinosaurs, curled in its nest, or standing watch over its herd, or floating in the dark waters of the deep ocean, its eyes closed, its breath slowing, its mind, whatever kind of mind it has, dimming toward rest. Two worlds, two timelines. The same night falling over both of them. The dinosaurs never asked why they existed. They never wondered about the asteroid that might have ended them or the alternative histories that might have unfolded. They lived.